We'll now talk about non-measurable sets. So recall, how did we construct the Lebesgue measure? We had P, which is consisting of all finite unions of the half-closed intervals, and then we constructed a ring out of it. This is just these intervals. Ring is finite unions of such intervals. On this we had a measure mu, and then we went to the hereditary sigma ring, which is H of R, which is nothing but the power set of the real line. Okay, and then we had the mu star measurable sets, which is nothing but the Lebesgue measurable sets, and then we had the Borel measurable sets, which are here. Okay, I gave you a indirect argument using cardinality that this is a strict inclusion, and then we will see in the next chapter a specific example of a set. So now we want to show that this is also a strict inclusion, namely there exist subsets of R which are not Lebesgue measurable. So that is what we want to do. So before we do that, so let us take x and y in 0, 1, and you define x sum y modulo 1. So this is addition modulo 1. So this is x plus y if x plus y is less than 1, and then it is x plus y minus 1 if x plus y is greater or equal to 1. So that the answer will come back into the closed, semi-closed open interval 0, 1. So if E is a subset of 0, 1, then and if y belongs to 0, 1, we write E plus y is equal to set of all x plus y, x is in E. Okay, so now we have the following lemma, which is based on the translation invariance of the Lebesgue measure. So E contained in 0, 1 and y belongs to 0, 1. If E is measurable, always remember when I say measurable, I mean Lebesgue measurable, then so is E plus y, and M1 of E plus y is the same as M1 of E. Okay, so proof. So we set E1, which is E intersection 0, 1 minus y, and E2 is equal to E intersection 1 minus y to 1. Okay, then E1 and E2 are obviously measurable, and because of this intersection they are disjoint. And therefore M1 of E is nothing but M1 of E1 plus M1 of E2, because E equals E1 union E2. Now by definition we have E1 plus y is the same as E1 plus y, because you are only adding up to 1 minus y, and any element plus 1 minus y, that will be strictly less than 1. Okay, and then similarly E2 plus y is nothing but E2 plus y minus 1, and these are just translation invariants. So M1 of E1 plus y So this implies that ei plus y are measurable, I equals 1, 2, and you also have m1 of e1 plus y, ei plus y, sorry, equals m1 of ei, I equals 1, 2. Okay. Now, ei plus y are disjoint. If not, there exists AB in 0, 1 such that A plus y equals B plus y minus 1, and this implies that mod of B minus A equal to 1, which is not possible because A and B are strictly less than 1. Okay, so then therefore you have E plus y equals E1 plus y union E2 plus y, and this is a disjoint union, and therefore E plus y is measurable, and m1 of E plus y is the sum of these two, and we know that's equal to m1 of E1 plus m2 of m1 of E2, and that's equal to m1 of E. Okay, so this proves the lemma. Okay. So now if xy belong to 0, 1, we say that x is related to y if x minus y is rational. So if we say that, then it say that this is rational. So clearly tilde is an equivalence relation. Okay, so 0, 1 gets partitioned into equivalence classes. Okay, so P equals a set containing exactly one representative from each equivalence class. So you have 0, 1 gets partitioned, that means a disjoint union of equivalence classes. Take one representative from each equivalence class. So obviously this is based on the axiom of choice. When you have such a thing that you can find such a set is precisely the statement of the axiom of choice. So we have you use two properties so far. One is the translation invariance of the Lebesgue measure, and the other is the axiom of choice. Okay, so now proposition P contained in 0, 1 defined above is not measurable, not Lebesgue measurable. So proof. So you said R naught equal to 0 and Ri numbering of rationals in 0, 1. It's a countable set, so you can number it. Only I put R naught equal to 0. So I said Pi equals P plus Ri. Okay. So then P naught is the same as P because it is 0, and if x belongs to Pi intersection Pj where I is not equal to j, okay, then x equals P1 plus R1 Ri, Pi plus Ri equals Pj plus Rj. So it will be P1 and P2. That will be Pi. Okay, Pi and Pj. So if Pi equal to Pj, then Ri is not equal to Rj, and therefore this equality implies that mod of Ri minus Rj equal to 1, and that's not possible. It's a contradiction. So this means Pi is not equal to Pj. But then Pi plus Ri equals Pj plus Rj. This implies that Pi is equivalent to Pj. Again, not possible, because these are they are distinct elements from distinct equivalence classes, and therefore this is also not possible. Okay, so we get that if I not equal to j, Pi intersection Pj has to be empty. Now, because P has one element from each equivalence class, and we have taken a numbering of all the rationals, therefore we have that union Pi I equals 0 to infinity is in fact equal to 0, 1. So if P is measurable, M1 of 0, 1, this is equal to 1, which is equal to sigma. So each Pi is measurable by the previous lemma. So this is equal to I equals 0 to infinity mu M1 of Pi, it's equal to sigma I equals 0 to infinity M1 of P. It's a constant sequence. So if this has to converge, then either all of them have to be 0. So this will be equal to plus infinity if M1P is positive, and 0 if M1P is equal to 0. Okay, so either infinity or 0, it cannot be equal to 1, therefore this is not possible, and therefore you have that P is not measurable. So we have explicitly constructed a subset of 0, 1 which is not measurable. Okay, so now let E be contained in P, E measurable, and you set EI equal to E plus Ri, and then you have that M1 of EI equals M1 of E for all I, and EI mutually destroy by the same argument. Now you have that sigma, so union EI is contained in 0, 1, and therefore you have sigma M1 of EI is strictly is less than or equal to 1. Okay, and this is equal to M1 of E for all I, and therefore this is possible only if M1 of E equal to 0. So only measurable subsets of P are subsets of measure 0. Same true for any Pi which is equal to P plus Rn. Okay, so say it will also have only this. Now let A be contained in 0, 1, measurable, and M1 of A strictly positive. Now you said EI equals A intersection PI. If EI is measurable, this implies that M1 of EI is 0. Because EI is a subset of PI, and we have seen the only measurable subsets of P or any PI are only sets of measure 0. And so if all EI are measurable, then A equals sigma sorry, union EI and therefore 0 less than M1 of A, which is less than or equal to sigma M1 of EI, I equals 1 to infinity, but that is 0. Okay, so you have another contradiction. Therefore, there exists at least one I such that A intersection PI equal to EI is not measurable. So implies A has a non-measurable subset. Now you can do this in any interval. So you can repeat all this in n plus 1. Okay, and therefore if A is contained in R, M1 of A is positive. This implies A intersection n plus 1 has positive measure for at least 1 n. And implies A has a subset which is not measurable. Okay, so every subset of R of positive measure has a non-measurable subset. So there are plenty of non-measurable subsets and therefore you have the strict inclusion. So again, let me recall for you. So you have P, the set of all intervals, and then you have R, the ring, and then you have the power set of the real line, which is the hereditary sigma ring, and then you have L1, which is Lebesgue measurable, and then you have B1, this is the Carotheo-Theodori construction. So we have shown that this is not true, and this also is strictly thing. This we will reinforce with a specific example later on, right now. Okay, so with this I will conclude this chapter on the Lebesgue measure. So before proceeding further, we will do some exercises next time.